When the James Webb Space Telescope opened its infrared eye, it immediately found a population of tiny, intensely red points of light that had been invisible to Hubble. These objects defy existing categories. They are far too bright for how small they are, and they glow in a deep infrared color that challenges current cosmic models. Explaining them as enormous crowds of ancient stars requires more matter than the early universe should have. Explaining them as ordinary galaxies behind a veil of dust fails because they lack the specific heat signature that thick dust produces. For 3 years, the data and the theories have remained at a standstill. Resolving this mismatch is now the central requirement for a coherent timeline of the early universe. The target for a breakthrough is an object called Glimpse 17775. It sits directly behind a massive galaxy cluster, whose gravity bends and focuses the light passing through it, magnifying the object by a factor of 2. This gravitational boost, combined with a 20-hour exposure from Webb, provided the equivalent of an 80-hour stare. No object of this class has ever been viewed with this level of sensitivity. Astronomers used that time to map the object's spectrum, the barcode of light that reveals chemical makeup, temperature, and movement. Every element prints a unique pattern of lines across the rainbow. While most red dots produce a smudged, unreadable signal, Glimpse 17775 returned a barcode with more than 40 distinct features. This allows the leading theory to be tested 5 different ways, simultaneously, on the same object. The depth of this data allows for a layer-by-layer reconstruction of the object's physical architecture. Look at the shape of the light signatures in this chart. Historically, wide bands of light meant gas was whirling at extreme speeds around a black hole, but that model fails to match the data here. Instead, the signal follows a soft, bell-shaped curve with spreading edges. Those spreading edges indicate that the light is bouncing and scrambling through a dense fog of electrical particles. The width is a measure of density, not speed. The data also shows a sudden drop in brightness, a cliff in the light, paired with a shadow. This is the signature of cool gas sitting in front of the source, swallowing light while blowing outward toward the observer. By looking at which electronic energy levels are occupied in these atoms, researchers can calculate the temperature of the gas. The upper rungs of the atomic ladder are nearly empty, indicating gas that is warm and crowded, rather than the fierce heat of an exposed black hole. These measurements point to a core buried deep inside a thick, churning cocoon. The signatures of a naked black hole are missing. This environment is further confirmed by helium shadows. One of these shadows is the deepest ever recorded in such an object, a unique feature that only appears when atoms are packed so tightly they are constantly jostling one another. The barcode also contains a pair of glowing oxygen colors. This specific glow is triggered by intense ultraviolet light from the center, yet the relative brightness of the two colors shows that there is no dust present. This absence of dust redefines the red color. These objects aren't red because they are hidden behind a filter. Instead, they are intrinsically red, because the light itself is continuously worked over and re-emitted by the thick gas cocoon. This environment also produces an iron forest, 16 separate iron signatures crowded into one section of the barcode. The iron pattern matches a prediction made in 2003 for gas being pumped by high-energy ultraviolet light. For 23 years, this was sheet music for an environment no one had actually seen. Glimpse 17775 plays the tune almost note for note. Because the light is scattered and re-emitted so many times by the gas, it loses the traditional signatures of a black hole and takes on the broad profile of a star. Every data point confirms this architecture, a core powered by a black hole wrapped in a cocoon that makes it look and act like a star. Correcting for fog density instead of speed proves the gravity holding the gas is much lower. The central black hole shrinks to 1/10 its assumed size. This lower mass solves the timeline crisis, perfectly fitting within the time available since the cosmos began. This smaller engine is feeding at twice the theoretical speed limit. It manages to stay intact because the weight of the surrounding cocoon holds the incoming material in place. The young universe was populated by these modest engines, running at full throttle while wrapped in their own protective shells. While the paper identifies the architecture, it leaves one question open. Where did this central core come from in such a young universe? There is no evidence of a preceding star that collapsed to form this core. The origin of the central engine remains unaddressed in the conventional literature. Nassim Haramein's unified physics framework provides a mechanism for this. It suggests that black holes are beginnings rather than endings, arising directly from the organized energy of the vacuum to act as the organizing centers for all surrounding matter. Glimpse 1777-5 follows this predicted pattern. A core appears first, and matter then organizes into an envelope around it. As this animation shows, the same architecture appears at every scale, from subatomic particles to galaxies. This object is a single data point in a universal scaling law. It shows that the architecture of a central core organizing a surrounding cocoon repeats throughout nature. Black holes didn't just appear in the early universe, they provided the structure for it to grow.